In this video, I want to dive right into Retrieval Augmented Generation, or RAG. RAG is based on the idea that large language models are trained on a large chunk of the internet, and they have a good understanding of a wide variety of concepts. But often, just like a human, they need to be reminded of certain ideas, or just haven't been exposed to certain information. So RAG empowers users to add additional context to an LLM that it hasn't previously been exposed to. And this could be your specific enterprise data that hasn't been exposed to the internet, or it could be newly released technical articles or documentation. Or it could be sensitive information that ChatGPT or a large language model has already been exposed to, but needs to be reminded of so that it doesn't make mistakes. Because again, large language models compress information, and that means that they're not as good at regurgitating information as something they've seen more recently. There are two key steps to this approach. The first is we want to extract the relevant data that we want the large language model to answer questions about. And the second is we want to feed additional data into a large language model's context window and have it generate a response based on that data. There are a few key frameworks for accomplishing this task of adding additional context to an LLM. The first is LangChain. LangChain is an open source framework that is built specifically for developers creating enterprise or production applications. So if you're working with large language models or vector databases, LangChain is just going to make the process a little bit easier. Now, you don't necessarily have to use these frameworks like LangChain, but they will simplify your code. And basically, the way these frameworks have been built over time is that developers were building things from scratch, and they wanted modules to help them with this kind of stuff. So if you're working with agents or memory, long-term memory, anything of this kind of sort with large language models, LangChain is built for that purpose, so you don't have to create all these methods from scratch. And it could do things like load data, process it, index it. It can help you create agents, create tools for your agents, create chains of multiple events with LLMs. It can help you retrieve data from your vector database. All these things is something LangChain has built up. And notice how it's a lot of things. It's a very robust library. Now, it has broader use cases than LlamaIndex, and it's a little bit more flexible because it's geared more towards developers building applications and less towards data science. LlamaIndex is a library that does a lot of the same things as LangChain, but it's a little bit more geared towards data science. That means it's good for extracting information, parsing it, retrieving it. And both of these frameworks work with KDB.AI, right? Both of these frameworks integrate a lot of different vector databases, and you could use them for all of KDB.AI's features, including time-based filtering. And for your use case, you could likely use either. So it depends on what specific library you prefer to use, what you have more experience with, which API is simpler for you, which documentation you've been more exposed to. For me personally, I use both depending on the application. For a lot of data science stuff, I do prefer to use LlamaIndex. But a lot of what you could do with these frameworks, you don't necessarily need them for. You could just write vanilla code without a framework. And for smaller applications, that'll be a little bit more effective because you won't have to install all these large libraries. So depending on the application, it might make sense not to use a framework at all. Now, RAG has a lot of different use cases, and they're mostly similar in practice. It's exposing your large language model to new data. For example, if I had an earnings call chatbot, I would be able to ask, what was NVIDIA revenue last quarter? And then I would be able to query my vector database, get that answer, and have my large language model be able to answer it accurately. Another use case for RAG is something like a clothing merchant chatbot, or any kind of chatbot that replaces a human in some way. And this kind of chatbot can answer a question like, what is the return policy for shoes? Something that is based on our internal data. This kind of chatbot typically replaces a human worker in some way, because otherwise a human would have to go and learn all of the documentation in our internal resources and be able to answer this question. And the most important thing with a chatbot like this is, are we accounting for the cost in the decrease in accuracy based on using a chatbot instead of a human. And what this means is a wrong answer from our chatbot has a certain cost, but we're saving a lot of money by replacing a human who's doing this task. So we have to calculate based on the percentage difference in terms of accuracy between our chatbot and a human. Is it still worth it to eat the cost of a potential bad response? And if you have a very accurate retrieval system, typically the answer is yes. A news chatbot is another use case that takes advantage of the fact that RAG can introduce new information to your large language model. For example, we could ask, what happened in the news today? What happened to NVIDIA stock today? What is going on in the news, right? For example. And the reason for this is that our large language model simply wasn't exposed to anything recently. These models were trained a long time ago, often more than a year ago. Another use case is a documentation chatbot, which could answer something along the lines of, how do I batch requests for this library? And often this kind of question can be answered with something that the large language model was introduced to in its training data, but the large language model itself can't do it very accurately. It needs to be reminded of that information, or it needs to be exposed to that again. It's the same way I am reading these slides as a person doing this presentation, and this is reminding me of what I'm going to talk about. So you want to introduce that information to a large language model to improve its performance on these kinds of questions. So we can imagine a naive RAG system where we have some data, we embed it, we generate some vectors, we insert that into our vector store, and then our user can ask a question like, what is the return policy for these shoes? And based on that, we could generate an embedding, do semantic search on our vector store, return relevant data, and then we could insert it into our large language model. And how we typically do this is we have some prompt, like act as a help desk worker. And after that prompt, we say, use the following information to answer the user query. And then we add the relevant contextual data. And then we add the query. What is the return policy for these shoes? And based on that, the large language model can generate a response that we could then show to the user. And this response is going to be grounded on our internal data. There are simple ways to improve this architecture. One is to introduce an agent. For example, here we are doing the same thing. We're taking data, embedding it, inserting it into our vector database. But then when a user asks a question, we can incorporate that question and the previous conversations to create with an agent a more robust question that we could search our vector database with. For example, let's imagine a conversation where the user was talking to the large language model about shoes and then asks, what is the return policy? The agent would have the context of the conversation and be able to reformat that query to what is the return policy of shoes in particular. And then it could use an additional tool like our vector database to retrieve a response and return that and process it and return that response to a user. It can also be introduced to many different tools. That's why ChatGPT is able to do so many things. Image generation, it can search the web. With a custom GPT, you could add a vector database and search your internal data. You could add files. The reason for that is that ChatGPT has an agent that is able to execute all these tools and process the information that is returned. And what's important here is that a large language model is actually really good at ranking things because it is list aware. It can understand, okay, this thing is better than this other thing, which you can't really do with traditional ranking with, say, a vector database. And that means when you return some re-rank results, it can re-rank based on the conversation of the user. So it can understand and show that user the most relevant results, not necessarily in the order it was exposed to it from the vector database, which is incredible. Like, you have an additional re-ranker just by introducing an agent. But sometimes you want even more robust re-ranking. And for that, you could use a specialized re-ranker. What a re-ranker does is it takes the 25 most relevant chunks from your vector database, and then it re-ranks those to get a more robust ordering. And then you could take the top 3, for example, and either display them to your user or insert that into an LLM to get a response. And this is used because vector search with a vector database is extremely fast. You could process millions or hundreds of millions of documents in milliseconds. But it's just not as robust as neural re-ranking methods. So these neural re-ranking methods are much slower, but can give you a more accurate ordering. And these re-rankers are typically cross-encoders, which are neural models that process queries and documents together, understand the specific relationships between them, and then output a score. The best performing re-rankers are currently closed source, and there's a few of them that perform extremely well, including Cohere Re-Rank, and Voyage.AI recently came out with a very well-performing re-ranker as well. But open source cross-encoders perform almost as well, and they have a specific advantage in that you could deploy them on your own infrastructure, which means they're going to give you faster results because closed source re-rankers typically batch requests, and that means they get responses in the tune of like 200 or 300 milliseconds sometimes. With open source cross-encoders, you could deploy it yourself and get those sweet 50 millisecond to 80 millisecond re-ranking results. Sometimes, if you have a really fast re-ranker that's open source, you could re-rank in under 10 milliseconds. And you could also place the re-ranker closer to your vector database in physical space, so you don't have that over the wire cost as well. So there are advantages, but this really takes a lot of MLOps experience to do. But the problem is that re-rankers in general typically have really high latency compared to vector search. So you really have to be careful and figure out whether this improvement in accuracy is worth the additional time that it takes to re-rank. But the increase in performance is usually great enough that it's actually worth it. Sometimes this performance boost can be over 20%, which means that if you can use a re-ranker, you probably should, but you should really think about latency as well. Cross-encoders are typically limited to around 1,000 documents, which means they're typically used at the end of your pipeline. So first you retrieve with your vector database, and then you re-rank with a cross-encoder. You could re-rank the last 25 results, you could re-rank 1,000 results, but you have to take into account, okay, how is your latency going to work? In theory, all these requests are parallelized, but in practice, the more documents you re-rank, the longer it's going to take. And there are other options like Colbert that offer very similar performance at lower latency, but these are a little bit less popular right now and a little bit harder to implement, and they have slightly worse performance than cross-encoders in practice. The thing about cross-encoders and re-rankers is that they take just one line of code to implement. For example, Cohere Re-Rank takes one line of code, you send the top 25 documents from your vector database, and you get a re-rank response. And cross-encoders output a score between 0 and 1. So what you could do is you could create your own cutoff and say, if a certain document matches this criteria, this cutoff of say 0.7, then we're going to feed it into an LLM. Otherwise, we're not going to include it in our context for a large language model. I really hope this video helped demystify retrieval augmented generation, and I'll see you in the next one.